You already know how a decision tree thinks. You've played it since childhood. It's 20 questions. Ask something with a yes or no answer. Follow the branch. Ask again. And after a handful of questions, you land on a confident guess. Stack those questions up, and each one branches the data in two. The whole chain forms a tree, questions inside, and a predicted class waiting at every leaf. Today, we focus on classification trees, the ones that output a class like approve or reject. Let's name the parts, because every rule from here on hangs on them. At the very top sits the root. The first question, seeing every training sample. Each answer sends a sample down an edge. By convention, yes goes left, no goes right, into a child node. A node that asks another question is an internal node, and a node that stops asking and simply commits to an answer is a leaf. Its prediction is just the majority class of the samples that reached it. Root, internal nodes, leaves. That is the entire skeleton. Here is the picture that makes a tree click. On the right is feature space. Two features, x1 across and x2 up. Every sample is a point living somewhere on this plane. A split is one question on one feature. Say, is x1 at most 3? On the left, that becomes the root of our tree. On the right, watch what it does to the plane. It draws a single vertical line at x1 equals 3 and slices the space into two half planes. Now split again, but only on the right half. Is x2 at most 3? That adds a horizontal line, but just inside the region where x1 was already above 3. Each new question cuts an existing rectangle along one axis. And there it is, the deep truth of every decision tree. Because each split tests a single feature against a threshold. The leaves carve feature space into axis-aligned rectangles. Boxes, always boxes, never a diagonal. One leaf, one box, one predicted class. So a tree is easy to draw. The hard, interesting question is which split to make at each step. To answer it, we need one number that says how mixed a node is. We call it impurity. Picture three nodes. This first one is all one class, pure, and a tree loves it. No more questions needed. Just call the class. The middle one leans one way, but is a little mixed. And the last is a perfect 50-50 split, the most uncertain a node can be. Impurity should be 0 on the left and largest on the right. Two formulas capture exactly that. Both start the same way. In a node, count each class, divide by the total, and you get the class probabilities pi. They're fractions between 0 and 1, and they add up to 1. The first measure is Gini impurity, 1 minus the sum of the squared probabilities. The second is entropy, borrowed from information theory, minus the sum of pi times the log, base 2 of pi, measured in bits. Notice the minus sign out front. Each log is negative, so the minus makes entropy positive. Let's compute one for real, a node with 3 positives and 1 negative. The probabilities are 3 quarters and 1 quarter. Gini is 1 minus 9 sixteenths plus 1 16th, 1 minus 10 sixteenths. That leaves 6 sixteenths, 0.375. A single clean number for how mixed this node is. To anchor facts to memorize. A pure node scores 0 on both. Nothing mixed at all. And a 50-50 node hits each measure's ceiling. Gini 1/2, entropy exactly 1 bit. Gini needs no logarithms, so it's a touch faster. Entropy is the information theory purist's choice. In practice, they pick almost the same splits. Now the payoff? A split is good if it makes the children purer than the parent. We measure that drop in impurity and call it information gain. First, the impurity after the split. Crucially, it's a weighted average of the two children. Each child's impurity times its share of the samples, n left over n and n right over n. A big child counts more than a tiny one. then the gain is simply the parent's impurity minus that weighted after impurity. The larger the gain, the better the split. That single quantity is the engine of the whole algorithm. One warning worth flagging now. You must weight the children. Averaging the two impurities straight, ignoring how many samples each holds, is the single most common mistake, and it can crown the wrong split. With gain in hand, growing a tree is a simple recipe, repeated over and over. At a node, try every feature and every sensible threshold, every candidate question you could ask. Score each by its information gain and keep the single best one. That's the greedy part. The best cut right now, no looking ahead. Split the samples into the two children the winning question defines. Then do the very same thing on each child, again and again, until a node is pure or too small to bother splitting. The tree grows itself. Hold on to the word greedy. Choosing the locally best split at every step does not guarantee the best tree overall. Greedy is not the same as globally optimal. It's fast and it works well, but it's a shortcut, and we accept that. Time for real numbers. Start with a parent node. 6 positives, 4 negatives, 10 samples. Its probabilities are not zero point 0.6 and not zero point 0.4. Plug them in. Entropy works out to 0.971 bits and Gini to 0.48. Now a candidate split lands 5 samples on each side. The left child 4 positives and 1 negative. The right 2 positives and 3 negatives. The left is fairly pure. Entropy 0.7 to 2. The right is exactly as mixed as the parent, 0.971. Weight them equally. Since each holds half the samples, the after impurity is 0.847. Subtract from the parent, and the information gain is 0.124 bits. A modest but genuine improvement. Gini tells the same story. The children score 0.32 and 0.48. The weighted after is 0.4, and the Gini gain is 0.08. Different scale, same verdict. This split helps. Now a decision. A fresh parent, 5 positives and 5 negatives. Dead even. So entropy 1 bit and Gini 1 half, both at their ceiling. Two candidate questions are on the table. Which one should the tree ask? Split A sends 4 positives and 1 negative left, and the mirror image right. Each child has entropy 0.7 to 2, so the gain is 1 minus that, 0.278 bits. A solid split. Split B is greedier still. It pushes every positive left and every negative right. Both children are perfectly pure, entropy 0, so the gain is the full 1 bit. The whole parent's uncertainty, wiped out in one question. So the tree picks split B without hesitation. 1 bit beats 0.278. It's the largest gain possible for this parent because it separates the classes completely. Your turn. Here is a node with 8 samples, 6 positive and 2 negative. Pause the video and work out its Gini impurity yourself before I do. I'll wait. Here's the walkthrough. 6 out of 8 is 0.75 and 2 out of 8 is 0.25. Gini is 1 minus 0.75 squared plus 0.25 squared. That's 1 minus 0.5625 plus 0.0625. 1 minus 0.625. So the Gini impurity is 0.375. If you got that, you've genuinely got this. Left unchecked, this greedy splitting has a dark side. A tree will happily keep asking questions until every leaf is perfectly pure. One sample per leaf if it must. Zero errors on the training data, and a disaster on new data. Such a deep tree has memorized the noise, not the pattern. That is overfitting, and decision trees are famously prone to it. The fixes all pull the tree back towards simplicity. Cap its depth, max depth, so it stops asking questions after a few levels, or refuse to split a node that holds too few samples. so it never carves rules out of 2 or 3 points. Or prune. Let the tree grow full, then snip back the branches that barely improve things. Each is a way of trading a little training accuracy for a lot of generalization. Trap 1 and the big one. Always wait. The children buy their sample counts. A straight average of the two impurities can hand the prize to the wrong split. Trap 2. Information gain is the parent's impurity minus the weighted after impurity, not just the children's impurity on its own. Trap 3. Greedy picks the best split at each step, but that chain of local wins isn't guaranteed to be the best possible tree. Trap 4. A single tree can only draw axis-aligned rectangles. For a slanted boundary, it's staircases. And it's unstable, small data changes can reshape the whole tree. Let's lock it all in. A decision tree is a chain of yes or no questions, and geometrically it carves feature space into axis-aligned boxes. At each node, we measure impurity, Gini, 1 minus the sum of squared probabilities, or entropy, minus the sum of p log p, 0 when pure, largest when evenly mixed. We choose splits by information gain, the parent's impurity minus the weighted impurity of its children. Largest gain wins, and we grow greedily, top down, then rein the tree in with pruning or a depth limit so it generalizes instead of memorizing. Ask the right questions, keep the leaves pure, and don't grow too deep. That's the decision tree.